But before doing that, let me see if I can switch the page. Just in case people might be interested to know a little bit about how Kaiser Permanente Washington Health Research Institute might be similar or different than other types of research settings, I thought I would just briefly share, one slide kind of about the place that I work at. And so the Research Institute where I work is sort of like a mini school of public health, where there's 40 doctoral level faculty members across a variety of scientific areas. So we study things like aging, behavioral and mental health, cancer prevention, health equity, and pharmacoepidemiology, among other areas. I also wanted to just really acknowledge my colleagues in the vaccine treatment evaluation unit for their role in leading the Moderna phase 1 clinical trial for the coronavirus vaccine. So that's one thing that we're all really, really proud of colleagues working on that. And so many of the studies benefit from the relationship that we have with KP. For example, some studies will have patients recruited either for like a cohort study or a clinical trial, or for observational studies, we'll be using oftentimes EHR or other administrative data sources on patients. We also do have a learning health system portfolio of research that's sort of driven by relations with health system partners and addressing questions that they're interested in. Most of the research is funded primarily from federal agencies like NIH, FDA, PCORI, and CDC, not much unlike other schools of public health. And we also have a biostat unit with 7 PhD investigators, as well as 12 PhD and master's level collaborative biostatistician analysts. And so I work as part of that unit, and we really are involved with most of the research studies that go on. For today's work, I wanted to acknowledge my collaborators from Kaiser Permanente Washington, as well as from the University of Washington, and our funding from NIH. So first, I'll give some background on spatial confounding, including the potential that spatial modeling has to actually increase bias. Usually we think of when we have confounding, we want to have approaches that are going to reduce confounding bias, but spatial modeling in certain settings can actually increase the bias. Our motivating contexts are electronic health record studies, and in particular, the Moving to Health study that I mentioned. And then I'll describe an exposure decomposition framework. And then I'll introduce some existing statistical methods to adjust for spatial confounding. And then I'll describe our proposed exposure penalized spline approach. Then I'll go over a simulation study to evaluate the methods, the application to our Moving to Health motivating study, and then some discussion. So as all of us who work on observational studies know, unmeasured confounding can pose a critical threat to many of these studies. For our context, we'll be focusing on epidemiological studies where we have outcomes measured at an individual or patient level. And in this case, we can have confounding occur at multiple different levels, including the individual level, or confounding can occur due to variation over time or over space. And the level, either one or more, at which confounding occurs depends on the sources of variability in the exposure. So for different types of exposure, we can have different types of confounding. So for spatial level exposures, confounding arises due to variability across different spatial locations, referred to as spatial confounding. And some examples of spatial level exposures include built environment or ambient air pollution. But we also could have individual level exposures where confounding can arise both due to spatially varying factors that may be patterned with exposure. One example being socioeconomic status, which often can cluster spatially. Or we can have confounding due to individual level factors that vary between individuals living in the same location. And so some of the examples of these could be smoking status or medication use. To make these types of exposures a little bit more concrete, here we'll focus on two examples that we'll later look at in the application. So this first example is whether a person has a supermarket within 1,600 meters of the home address. And this 1,600 meters is about a 10-minute walk. So in this map, which is part of King County in Washington, and Seattle, if you're not familiar with the area, is this part right here of the county. The places in yellow are those that have a supermarket within a 10-minute walk, and red are those that do not have a supermarket. And then as an example of a person level or an individual level exposure, one example is smoking status. And so for each patient who live in different places in King County, we have a measure of whether they're a smoker, current, former, or never. And so it's not a purely spatial exposure, but as you can see from plotting the smoking status, this is the proportion who are former smokers. You can see that there is a spatial pattern with people who live in the northern part are a little bit less likely to be former smoker, or a little bit more likely to be former smokers relative to current smokers, and in the southern part of the county more likely to be current relative to former smokers. And so we can have spatial variability in individual level exposures. So what are some spatial modeling approaches that could be considered to adjust for spatial confounding? Well, one idea is that you could fit a spatial model to explain spatial variability in the outcome that may also be in the exposure and hence adjust for spatial confounding. And so you can do that either through a random effect model, such as a Gaussian process model with a spatial covariance, or through a fixed effect. So you could adjust for spatial location, and you can do that flexibly using spline terms. However, there's some literature that shows that when fitting a spatial model, there's actually a potential that you can increase bias as compared to fitting a non-spatial model. And this increased bias can occur even if there's an important unmeasured confounder. And so this seems a little bit counterintuitive. We're used to methods reducing bias, but the reason that this can occur is due to collinearity of the spatial term with the exposure of interest, if exposure varies highly spatially. So going into a little bit more detail on the prior literature, Hodges and Reich in a 2010 paper illustrated this potential for increased bias. And they argued that merely including a spatial random effect in the regression model is not a substitute for adjusting for unmeasured spatial confounding. And so that shouldn't be our goal in fitting this type of model. And given this, they propose an alternate spatial modeling approach called restricted spatial regression. And the idea behind this approach is that it constrains the random effect to be orthogonal to the fixed effect. And what this does is that this attributes all spatial variability on which the random effect and the fixed effect are competing to the fixed effect. And what this ends up doing is it ends up estimating the same fixed effect as the non-spatial model, but with the variance adjusted to account for the fact that we don't have totally independent observations. They may be correlated closer in space. Pachorik in 2010 furthered this literature and characterized the scenarios in which the increased bias can occur. And they found that the scenario of increased bias occurs when the spatial scale of the confounded variability in the exposure is smaller than the spatial scale of the unconfounded variability. And in this context, the spatial scale refers to the distance at which variation occurs. And so you can have a large spatial scale, which would be a sort of regional variability, or a fine spatial scale, which would correspond to local or neighborhood level variability. Then in the discussion section of this paper, they make the point that the scenario where bias is increased may be of limited practical interest because it's not clear that there are real applications in which the unconfounded variation in the exposure occurs at larger scales than the confounded variation. So they sort of say that there are these scenarios where you can have increased bias, but maybe these scenarios aren't that important. But from my perspective, I found this a little bit not something that I felt like I could necessarily go with applying these standard spatial modeling approaches, because there does appear to be this uncertainty about whether you could increase bias inadvertently. And so given this potential for increased bias, along with uncertainty around your given application is in the scenario of increasing bias, there's sort of this gap in knowledge of whether you should be applying these standard spatial modeling approaches. By standard, I mean the non-restricted approaches. And then another gap in the literature is that this prior work focused on purely spatial exposures. And so the extent to which the spatial modeling approaches could increase bias for individual level exposures that have both spatial and non-spatial variability hasn't been established or really looked at much. So as I mentioned, our motivating context for thinking about this issue are from electronic health records or EHR studies. And so EHRs really provide a really rich source of data for conducting observational studies in large populations. And there's a wealth of information, including demographic data, clinical measures such as blood pressure and weight measures, as well as diagnoses, prescriptions, and procedures. At the same time as there's this richness in the data, there's also certain types of data that are not routinely or commonly found in the EHR. And in particular, EHR studies will often lack detailed information on unmeasured spatial confounders such as socioeconomic status or SES. There are some measures in the EHR that may be associated with or capture aspects of SES, such as race, ethnicity, or insurance status. And in addition, information on a person's home address can be linked to census data, but this is typically done at a relatively coarse geographical scale, such as linking zip code to census-based measures. And so residual spatial confounding at finer scales is likely to remain in many EHR studies. For our particular example of moving to health, this was a study that links data on the built environment with longitudinal EHR data from KP Washington, which is an integrated healthcare system in Washington state. And one of the advantages of this moving to health study is that it provides a natural laboratory to investigate the impact of unmeasured spatial confounding in EHR studies, because we have a large population of patients with precisely geocoded addresses. There's also rich data on a large number of spatially varying risk factors, such as built environment measures. And we have fine individual level data on SES that's not available in a typical EHR study, because in our geocoding process, we were able to geocode to the rooftop level, which is not a standard data element in EHR. You might have the zip code, or you might have a very coarse or unrefined geocoding process, but with the rooftop level geocode, we were able to link to parcel level home property values to get a measure of individual level SES. But one of the challenging features of this is that it's a big spatial data set with about 120,000 participants. I'll next introduce some of the notation that we'll be using. And so again, we're focusing on a person level or point process data set where I indexes the person from 1 to n. We assume that there's been a geocoding process such that we have a spatial coordinate for each person. And then we'll let y denote the health outcome, x the exposure, and zc will be an unmeasured spatially varying confounder. And then we'll also denote by c a vector of potential measured confounders that could be adjusted for. Then for our exposure decomposition framework, we assume that our exposure of interest, x for person who resides at location si, can be decomposed into xs, which is a purely spatial component. And what this means is that for two individuals at the same spatial location, they'll have the same exposure, same value of exposure. So for si equal to sj, we'll have x of si equals x of sj for the spatial component. And then we also have independent component epsilon x, which has no spatial correlation to it. We can further denote the variance of the spatial and non-spatial components by v sub s and v sub epsilon. And then we'll define PNS to be the proportion of variability in the exposure that's due to non-spatial variability. And so just to note, in this exposure decomposition framework, this includes the setting considered by prior studies where you have no non-spatial variability. So the purely spatial exposures would be that you would have the variance of this non-spatial component would be 0. You just have the spatial component. So I just want to make a couple of notes here. So one is that you may have some spatial exposures that are available at an individual level. For example, you might perform a spatial model in order to try to get at exposure at an individual location. So this is often done through like mapping various variables to get and monitoring data to get point level predictions. But this would still be part of the purely spatial component, because for any two individuals, they would have the same value of the exposure if they lived at the same location. The key point of this exposure decomposition framework is that each component is subject to confounding at different levels. And so the XS, the spatial component, is clearly subject to spatial confounding. The epsilon X is subject to non-spatial or person level confounding. And for the purpose of this talk, I'm going to assume that there's no unmeasured person level confounders. So we have all the important person level confounders in our covariate vector C, but we may have an unmeasured spatial confounder. So then for our analytic framework that we'll be using to look at the association between our exposures and our outcomes, we're considering spatial regression models of this form, where beta is the parameter of interest that denotes the association between the exposure X and the outcome Y. Gamma C adjusts for measured confounders, and that could be done non-linearly. And then G of S is the spatially structured variability, which can be modeled either using a spatial random effect or using then the epsilon Y is just the residual error assumed to be IID across individuals. So for this analytic framework, for the setting where you have a purely spatial exposure, in Pechoric paper, they mentioned this point, that if the spatial term G of S is unconstrained, and terms beta X and the spatial term G are not identifiable. And the reason for this is that you could define an alternate spatial term G star without changing the likelihood. In particular, if G is unconstrained, we could define G star to be equal to beta times the spatial component XS plus G. And so this varies purely spatially. And then in the purely spatial setting, then the spatial component is equal to our exposure. And so G star is equal to beta X plus G of S. And so what this means is that it's hard for the data to distinguish between these two terms without having some constraints on G. In contrast, for an individual level exposure, the parameter of interest beta is identifiable without constraints. So taking that same G star function here, we would then be estimating the association between the non-spatial component and the outcome. So even if G is unconstrained, we could still estimate beta, and it's identifiable from this model. So just to sort of highlight for later when we introduce the exposure penalized spline approach, this is sort of providing some motivation for that approach. What this does is this suggests that if we can control for the spatial variability in our exposure X, such that the spatial component of the exposure gets incorporated into the spatially structured term G star, then this could enable us to estimate the exposure outcome association of the non-spatial component epsilon X, which is not spatially, doesn't vary spatially, and hence it's not confounded because our confounding. So before defining the EPS approach, I'm next going to describe some of the existing spatial modeling approaches that could be used to adjust for unmeasured spatial confounding that we'll be comparing in the simulation study. So I mentioned that sort of two general classes of spatial modeling approaches, one being a spatial random effect model, also referred to as a spatial generalized linear mixed model, or spatial GLMM. And so for the spatial GLMM, we can write out the order of spatial terms, G of S1 through G of Sn, and that's assumed to follow a Gaussian process with mean 0 and a spatial variance covariance matrix. And so in particular, the variance V of theta has ij element equal to Vij, which depends on the spatial coordinates Si and Sj, and also has a vector of parameters to be estimated. And so here V is just a spatial covariance function, such as a Matern. And inference is typically conducted as Bayesian, and model fitting is typically done via Markov chain Monte Carlo, or MCMC. As I mentioned, our motivating context is a big EHR data study, and spatial GLMM in their standard form are very challenging to fit to big data sets. And the reason for this is that you need to compute the determinant and inverse of an n by n matrix, where n is the number of observations at each iteration. And so with a really large data set, you might not even be able to compute the inverse a single time, much less have to do it repeatedly, which can be really slow, even if it's able to be done. And so there's been a range of different methods that have been proposed to fit spatial GLMM to big data sets, including low rank approaches, covariance tapering, There's also approximations using Gaussian Markov random fields, such as that's implemented through the INLA R package. And then there's nearest neighbors models. And this is really an active area of research to try to come up with efficient approaches. For today's work, we focused on one of these methods, which is the nearest neighbor Gaussian process, or NNGP models. Without going into too much detail, just to give a brief overview of how this approach works, the idea is that it constructs an NNGP covariance function V tilde such that its inverse is sparse. And the way it's done is that you select the number m of nearest neighbors or points that are used to construct the process at each spatial location. In a 2016 by Data and colleagues, they showed that it's able to well approximate the underlying full Gaussian process. It's also been shown to have good predictive ability and accurate uncertainty quantification on a simulated and real data set as part of a case study composition that's described by Heaton et al. In 2019. And there's several different methods that perform well, and this is just one of them that had very good performance. It's also nice because there's an easy to use software implementation that's described in a paper on arXiv that's been easy to apply and use. So we talked about the spatial generalized linear mixed models, and then there's also spatial spline models that we could consider. And so instead of modeling G as a random effect, for the spatial spline models, we could model G as a smooth function of the spatial location. A popular choice for doing that flexibly is through splines. We focused on thin plate regression splines, which have a few advantages, including being computationally efficient for large data sets, and you also don't need to specify not locations, which is a nice feature of these. And then the degree of spatial smoothing in the G function is controlled by the number of degrees of freedom, or DF, of the spline terms. And you have a couple of options for that. You could either specify the number of spatial degrees of freedom a priori using a fixed degree of freedom model, or you could use a method in which the data determines the degree of spatial smoothing, such as through a penalized spline or PS model. These models are also referred to as spatial generalized additive models, spatial GAM. Going into a little bit more detail on the specific sort of implementations of these models. So for the fixed degree of freedom model, our smooth function of spatial location G depends on the dimension of the spline basis, K. And here the spatial degrees of freedom is simply equal to K minus 1, with 1 degree of freedom being lost to the identifiability constraints. And then different values of the degree of freedom that the user specifies would then adjust for spatial variability at different scales. So if you specified a small degree of freedom or a small basis dimension, then you would be adjusting for large scale spatial variability. Whereas if you adjust for a large number of spatial degrees of freedom, then you're adjusting at finer and finer spatial scales. But you may not feel comfortable specifying what degree of freedom you think the confounding is occurring at. And so an alternate approach is to do a data-driven approach to determine the degree of freedom. And so for penalized spline models, these are where you estimate the spatial smoothing parameter lambda y. And there's different criteria you could use to estimate it, but the common implementation is to use generalized cross-validation criterion, or GCV. You still have to specify the number of basis dimensions K, but in practice, if you select large K, then the estimated smooth term G will not generally be dependent on that choice of K. In practice, it's good to check for your particular data set that you've chosen K large enough. One way to do that is to look at the estimated degrees of freedom from the model, and if it's very close to K, then you probably should try a larger value of K. And so those are sort of existing spatial modeling approaches that can be applied to large data sets. For the exposure penalized spline approach, it's a little bit different. It's a two-step approach where we first fit an exposure model. It's a similar structure to the outcome model, and we could adjust for the same covariate C. And here we have, this is the spatial term, so it's a function of the spatial location. And we have the smoothing parameter lambda x because it's selected to explain spatial variability in the exposure. And then we use the estimated smoothing parameter from the exposure model directly in the outcome regression model. So our G will depend on lambda x hat, since it's estimated from the exposure model, plus number of basis dimensions. So again, the degree of spatial smoothing from the EPS approach is selected to explain spatial variability in the exposure. And so the idea is that this then would estimate the association between residual or non-spatial variability in the exposure and with the outcome. And as I mentioned earlier, the goal is that residual variability in the exposure would then comprise predominantly non-spatial variability and hence non-spatially confounded variability. So that's our approach in a nutshell. Are there any questions so far before moving on?
Yes, can I ask a quick question?
Yes, please.
Thanks, Jennifer, this is great. Just for clarity, are you thinking of anything temporal as sort of fitting in that non-spatial part?
Yeah, so for now, I've not been focused on temporal variability. For our specific exposure of the built environment, we do have some temporal variability, but most of the variability is due to the spatial variability. But I think that's a really good point for sort of future works. I think exposure could be probably decomposed into 3 components if you thought that temporal variability was a large contributor. But in this case, that could be absorbed into the non-spatial component.
Okay, thank you so much.
Great question.
I've got a quick question too. Hi Jennifer, good to see you.
Nice to see you.
I'm trying to think about sort of implications for power, and because it seems like you're decomposing into the spatial component and the non-spatial component. And I'm trying to understand if something varies only spatially, can we not look? Can we not find its association then because it's kind of aliased with the spatial confounding?
Yeah,
I'm trying to think about.
We'll kind of see that when we get to the simulation, but essentially, yeah, you can easily have the situation where you can increase bias by adjusting for the spatial location. And so if you are concerned with spatial confounding with those exposures, then you may not be able to actually adjust for spatial confounding through modeling. You might need to either try to measure the confounder or do some like a sensitivity analysis approach and say that we're estimating the association, we're not adjusting for unmeasured confounding, and address it in other ways. Because they are, fitting the spatial model when you have a purely spatial exposure, it can cause things to really blow up. You'll kind of see you can get really large variability in the estimates as well.
Thank you.
So I think I'll move forward, and hopefully we'll have, even though I joined late, hopefully we'll also have a good time for questions at the end. And I'm also able to stay later if folks would like. So for the simulation study, again, our outcome is given by Y and our exposure X, and then we have the spatially varying confounder ZC. And so our outcome model, our data generating model, our outcome depends on the exposure X. It depends on the confounder ZC with some error. And then our exposure has 3 different components. It has 2 spatial components, ZU and ZC. And ZU is an unconfounded component that varies spatially. And then ZC is a confounded component that varies spatially. You can see that ZC appears in both the exposure and the outcome model since it is a confounder. And then we have some exposure error. For the unconfounded and confounded components of exposure, we generated spatially correlated components from a mean zero Gaussian process with matern spatial covariance. And here is showing a single realization from the data generating model. And we varied the spatial range parameter phi u and phi c, where we considered 3 different values. We considered fine scale variability, so 0.04, from moderate spatial variability, 0.15, and then large spatial scale of 0.6 that might correspond more to regional variability. For our exposure generating model, we also varied the variance of our non-spatial component, a sigma squared x. And then we considered 3 different scenarios of the proportion of non-spatial variability in the exposure. We considered having no non-spatial variability, which corresponds to the purely spatial exposures. And then we considered 2 scenarios having non-spatial variability, one with low non-spatial variability, So this would be where the exposure is mostly spatially varying, but there's a little bit of non-spatial variability. And an example I can kind of think of in this scenario would be if you're trying to get at individual level air pollution exposure, because we all have our ambient levels, but then our individual exposure is different from our ambient levels. So we might have some non-spatial variability. And then we also considered a scenario of moderate non-spatial variability of 50%. And so the individual level exposures could correspond to things like air pollution or blood pressure. For our comparator approaches, we considered a non-spatial model. We considered different fixed degree of freedom spline models, adjusting just for a few spatial degrees of freedom all the way up to 1,000, which is quite a lot because we're only going to consider data sets of 2,500 observations. So it's really using a lot of degrees of freedom to see how far we can push these models. And then for penalized spline models, we considered both a PS, the sort of traditional penalized spline approach, and the EPS with 500 or 1,000 basis dimension K. And then for the nearest neighbor Gaussian process, we considered M equals 10 nearest neighbors, which was shown in that DOTSAT paper to provide a good compromise between computational efficiency and providing a really good fit to the data. And then just to note again, for the PS, EPS, and NNGP approaches, the degree of spatial smoothing is estimated from the data, in contrast to the fixed degree of freedom approaches where it's specified by that, where it's controlled by this value K. So just the general sort of setup of the simulation study, we generated 100 data sets for each scenario of 2,500 observations each, using the data generating model that we've talked about. And then to each simulated data set, we fit each of the comparator approaches, where for all of the approaches, we fit them without the confounder ZC. So this was an unmeasured confounder that we don't have for any of the methods. And then we evaluated the performance in terms of bias and root mean square error and estimating the parameter of interest beta, uncertainty quantification, and computation time. So for the first set of results, we'll focus on the scenario of having no non-spatial variability. So these are the purely spatial exposures that were the focus of prior literature. And so to orient you to this plot, it's a little bit busy, but we'll have a similar plot in the next couple of slides. Each of these panels corresponds to a different setting of the spatial range parameter of the confounded component phi C and the unconfounded component phi U. And these upper quadrant here corresponds to that setting where bias is increased, according to prior literature. So that's a setting where the spatial scale of the unconfounded component is larger than the spatial scale of the confounded component. This red point is the non-spatial model. And then in our simulation setup, the true parameter beta was 3 down here. And so the non-spatial model is biased with an estimate of 4. And then in this scenario, which we sort of expected from prior work to have potential for increased bias due to spatial modeling, we can really see that clearly. As we adjust for more and more spatial degrees of freedom, we get bias for even larger, going up to 5, where again, our estimate is 3. And the NNGP approach is between the non-spatial model and sort of the very fully adjusted fixed degree of freedom model. In contrast, as we sort of expected ahead of time, we can see that when the spatial scale, the confounded variability is at a larger scale than at the unconfounded variability in the exposure, we do see, in contrast, we are able to reduce bias. So the estimate is able to go as we do further and further adjustment for spatial degrees of freedom. We can get the truth, which is 3. But we do have a lot of variability because we're adjusting for a lot of degrees of freedom. When we have 25 observations, we have 1,000 up to here, 1,000 parameters being estimated. And again, the PS, EPS, and NNGP approaches are in between the non-spatial and sort of the fully adjusted spatial model. And then lastly, along the diagonal where the spatial range of the two components are the same, we see that the estimates from the spatial model are the same as from the non-spatial model. So we don't increase or decrease bias, though we do increase a lot of variability. So that would affect our mean square error. And so really in the scenario when you have purely spatial exposures, in certain circumstances, spatial modeling can help you, but it's still not clear to me that you necessarily know that you're in those scenarios. And so there is this risk of increased bias that you would have in the setting of purely spatial exposures. And now the story is a bit different once we allow for non-spatial variability. So this is jumping to the scenario where we have moderate or 50% non-spatial variability in the exposure. And then for all of the settings, we can see that as you adjust for more and more degrees of freedom, they're all able to eventually eliminate all of the bias. And then the models that are estimating the degrees of freedom, again, fall between the non-spatial model and sort of fully or maximally adjusted spatial model here, up to 1,000 degrees of freedom. So even in this scenario that was hard in the purely spatial setting, not in all circumstances, but in many circumstances, bias is able to be reduced by spatial modeling. And then in this diagonal setting where we weren't able to increase or decrease bias, when we had a purely spatial exposure, we're able to do a pretty good job at decreasing bias when fitting a spatial model. And then the scenarios that we did well in the purely spatial scenario, we continue to do well when we have non-spatial variability. And so what this shows is that even for the harder scenario where the spatial scale of the unconfounded component is larger than the confounded component, spatial methods generally do not increase bias in our simulation study. So this final kind of plot along these lines is just showing for this hardest scenario, this most challenging scenario where we have very fine scale confounded variability, and then a large scale unconfounded variability as we go from as we increase the proportion of non-spatial variability from none to low to moderate. And again, this was the plot where we saw that we were increasing bias in all the spatial modeling. With low non-spatial variability, when you adjust for some spatial degrees of freedom, you do increase bias, but then with further adjustment for spatial variability, you can then go down and decrease bias again. And then for the setting of moderate non-spatial variability that we looked at, there are still some spatial models that have increased bias, but then as you continue to adjust, you're able to remove the confounding bias due to this fine scale spatial variability. So, and again, this is highlighting the challenging scenario, and those other scenarios, the spatial models were all less biased than the non-spatial model, provided that you had some non-spatial variability in the exposure. So in terms of mean square error, because we saw that if we just fit the model with 1,000 degrees of freedom, that really, really full model with many, many parameters, we could remove a lot of bias, but we could also have potentially increased variability. And so we want to strike a balance and get the method with the optimal root mean square error. So in terms of the fixed degree of freedom model, the optimal number of degrees of freedom for adjustment depended on the spatial scale of the unmeasured confounder. And you may have prior knowledge of what the spatial scale is, but you may not. And so in our specific scenario, it was about 50 degrees of freedom for the high scale confounding, about 250 degrees of freedom for confounding at a moderate spatial scale, and 1,000 or even more degrees of freedom when you had really fine scale variability in the unmeasured confounder. But in practice, we might not know what the actual optimal degrees of freedom is. And so using a method that can estimate the spatial degrees of freedom to target confounding adjustment can help us in mean square error. And so we found that the exposure penalized approach did pretty well in getting mean square error close to the optimal. And so looking at this sort of challenging setting, the blue points are the moderate non-spatial variability, and the green triangles are the low non-spatial variability. And we can see that the exposure penalized spline does pretty well, getting close to the optimal adjustment. And then for the setting of low non-spatial variability, again, the exposure penalized spline approach got the closest to the optimal in terms of the number of spatial degrees of freedom. So just again, a high level summary, when there was no non-spatial variability, again, our purely spatial exposure, the spatial models could either increase or decrease bias. As long as there was some non-spatial variability for the individual level exposures, the spatial modeling was generally no more biased, and in most cases, it was substantially less biased than the non-spatial model. For the RMSE, among the data-driven approaches to determine the degree of spatial smoothing, we found that the EPS approach had the RMSE closest to the optimal and always outperformed the non-spatial model. In terms of uncertainty quantification, I didn't show the plot here, but we found that the penalized spline approach tended to underestimate the variability, which makes sense if you think of the fact that it's using the same model to both estimate the spatial degrees of freedom and to fit the outcome model. So we're sort of doing model selection and estimation from the same model. And the EPS and NNGP approach tended to somewhat overestimate the variability. So the credible intervals were a little bit too wide. For the median computational time across all the simulation scenarios, all the methods were under 6 minutes. The NNGP approach can be speeded up by doing over multiple processors, so it has potential for computational improvement. So now moving to health application. So the goal of the study is to estimate the cross-sectional and longitudinal associations of residential built environment on both weight and type 2 diabetes. For illustration for this talk, we focused on cross-sectional association with the body weight outcome for the supermarket measure and the smoking status measure that I showed previously. So the supermarket measure is one of our built environment measures of interest. And these are obtained for each point in space, looking to see whether there's a supermarket within a 1,600 meter radius of that. And it's using actually a network-based measure that you could walk or drive. And so because these are spatial maps that are obtained in different calendar years, and there's very little variation over time, sort of addressing Rima's question from before, this is pretty close to a purely spatial exposure. There's a little bit of temporal variability, but the proportion of non-spatial variability is practically zero. Because from our simulation studies, there was sort of suggestion that bias could be increased in this scenario. For illustration, we also considered one of the individual level risk factors from the study. And so for illustration, we just focused on smoking status, which is current, former, or never smoking. And then we focused on the comparison of former smokers versus current smokers. And for this individual level exposure, we estimate how much non-spatial variability there is in the exposure. We fit an unadjusted spatial GAM with a different number of knots. And we estimated from those spatial GAM that the proportion of spatial variability was about 3%. And so there's pretty high non-spatial variability of around 97% non-spatial variability. So there's some, you can see the spatial patterning, but most of the variability is non-spatial in this particular exposure. And so, as I mentioned, for EHR studies, there's potential for confounding due to SES factors. And in the study, we actually have a measure of SES at an individual level. We have property values. And so we could observe that the property values were highly associated with the supermarket measure, with smoking status, and with body weight. And so if a study doesn't have a measure of SES, they could have biased estimates. But on the other hand, we can also see that there's some spatial correlation between many of these measures. And so perhaps a model that can adjust for spatial variability would be able to explain some of the confounding due to property values. And so just to illustrate some of the spatial patterning for weight, we see that individuals in more northern regions of the county tended to have lower weights as compared to individuals in more southern regions. Individuals in more northern regions tended to have a higher likelihood of being a former smoker as compared to being a current smoker. For property values, there's a little bit interesting spatial pattern. It's not necessarily, there's some north-south gradient, but there's also, you can really see a gradient close to the water areas, which makes sense. Places close to the water have higher property values typically, which is interesting for supermarkets because there's fewer supermarkets close to the water areas. They tend to be more in the urban setting. So there's some north-south gradient with the supermarkets too, but there's also a little bit of the water area that relates to the property values. So there's some interesting spatial correlations in these data. Okay, so I'll try to wrap up soon because I know we're close to the end of the hour. But for the application, we applied different degrees of covariate adjustment. We considered a base model that adjusted for sex and spline terms of age and height, a standard model that included the above plus insurance status and race ethnicity, which are commonly available in EHR data. And then we also, what we call the ideal model, which is the above plus spline terms of property value, which is a higher quality measure of SES than is typically available for many EHR data studies. And so what I want to just focus on first is that as we go from the base to standard to ideal model, if we focus on the non-spatial model, the estimates sort of increase in magnitude. So they go from about a little bit below -3 to close to -4 as you adjust for in the standard model and then the ideal model. If you look at the spatial modeling, what's happening to that? The estimates are jumping. They're jumping, going from negative to going positive. And it's happening in the opposite direction that the property value adjustment is happening. And so, I mean, it's possible that maybe this is due to some other unmeasured confounder that we don't have. So maybe it is happening in the right direction, but more likely we think that this is probably an artifact of increasing bias due to the collinearity. In contrast, if we look at the smoking status individual level factor, again, going from the base to the standard to the ideal, we can see that in the non-spatial model, the estimate goes from about 1.5 to about 3.5. So adjusting for insurance status, race, ethnicity, and then property value increases in magnitude, the estimate. And here we can see that the spatial models are moving the estimate in the same direction as the property value adjustment. And then in particular, we can see that under the standard model, estimates that we're getting under spatially adjusted models are pretty close actually to the estimate that we get under this ideal property value adjusted model. I think another interesting finding is that even under this quote unquote ideal model, we can still see that further spatial degrees of freedom changes the estimate even more, increases it in magnitude even more. And we think that this is very likely due to other aspects of SES that aren't captured by property values. As happy as we were to have the property value measure, it's really not capturing things like educational attainment and other factors that are capturing SES. So these results suggest that fitting a spatial model has the potential to substantially reduce bias. So just to conclude with a few sort of summary of the findings and some additional context. This work builds upon prior literature on spatial confounding that focused on settings of purely spatial exposures. And we distinguish between two types of exposure that are common in epidemiological studies with outcomes at a person level. We proposed a framework in which the exposure of interest could be decomposed into spatial and non-spatial components. And then we conducted simulation studies in which we varied the relative contributions of these two components. We found that in contrast to those prior settings where the exposure of interest is a purely spatial exposure, when there's an individual level factor that has both spatial and non-spatial variability, that the potential for these standard spatial modeling approaches to increase bias appeared to be quite limited in those cases. And in those cases, the spatial modeling approaches have the potential to greatly reduce or even remove spatial confounding bias entirely. In addition, from our simulations, we saw that the higher the proportion of non-spatial variability, which is a quantity that we can estimate, the greater the potential that bias will be reduced. And so you can kind of get a sense when you look at your exposure data, am I in that setting where bias could be increased or decreased, or can I be in that setting where bias is likely to be reduced? And then we proposed the EPS approach to control for spatial confounding. And this approach addresses the fact that the spatial scale that's most associated with variability in the outcome, which would be the spatial scale that would be selected by the standard penalized spline approach, that type of spatial scale may not fully adjust for the variability at the scale that's most confounded. And so this is actually an issue that's well known for variable selection and methods, not spatial specific, that target outcome model fitting relative to statistical methods that are directly developed to target confounding adjustment. So in the non-spatial setting, as an example of this paper is the Bayesian adjustment for confounding, which shows that you can get better estimates than you can by using regular variable selection methods. But to our knowledge, approaches to select the spatial smoothing parameter in order to target the confounding adjustment in this common setting of individual level exposures hadn't been considered previously. For these types of exposures, the EPS approach is able to remove the confounded spatial variability in the exposure so that you can estimate the exposure outcome association of the non-spatial and therefore non-spatially confounded component. In our simulation studies of the individual level exposures, we found that when there was an unmeasured spatial confounder, that the EPS approach achieved the best performance of all of the data-driven methods to estimating the spatial degrees of freedom. So in terms of our moving to health application, we found that the environment exposures that were of primary interest, because they varied almost purely spatially, we were hesitant to apply those spatial modeling approaches out of concern that bias could be increased. So originally we thought, well, we have property values, but there's probably other unmeasured confounding. In addition, we have spatial variability, so we should fit these spatial modeling. After doing these explorations, we opted not to do that for the primary analysis. And so with big EHR data studies becoming increasingly common, we really need methods to address this unmeasured confounding due to SES. And we need computationally efficient modeling approaches that specifically target the confounding adjustment. And so our results highlight that EHR data studies that consider the health effects of individually varying exposures could benefit from spatial modeling in order to reduce bias due to unmeasured confounders like SES. And so, yeah, sorry for rushing a bit at the end, and thanks again for your attention. Welcome questions and discussion.
Well, thank you so much, Jennifer. Brilliant talk. I'm still kind of reeling, trying to get my intuition straight about how spatial confounding can increase rather than, I mean, adjustment for spatial confounding can make matters worse. I'm going to have to think about that some more.
Yeah, it still hurts my head too, a little bit.
It's very counterintuitive. Questions from anybody else? I think we can just keep the Zoom open as long as we'd like.
Jennifer, that was a great talk. I'm Dan Tancredi. I'm from UC Davis. I didn't quite follow whether or not in your simulations you were able to decompose the effect, for example, of SES. We often think of the individual level effect of SES as being different than the area level effect. And so an interesting kind of simulation would be to posit that there are both area level effects and individual level effects, and they differ in the regression coefficient. And so as I understand it, one of the approaches you consider tries to isolate the within area effect, the individual level effect of SES. And those kinds of parameters would, if they're different, if the actual simulation, of course, makes it so that the individual level effect has a different coefficient than the area level effect, then you'll have different estimates if you do account for that versus if you don't. But I'm not quite sure if in your simulations you set up a situation where there were actually different levels of different effects of SES depending on if it's at the area level or at the individual level.
Yeah, so for the exposure model, I focused on the setting where you have just a single spatially varying confounder.
Okay.
And so ZC. And so if you think about property values, that's actually a little bit different because it's not property values, there's an individual level aspect to it. And then there's also sort of the spatial clustering of the property values that when we saw that spatial map, you can see that there is a lot of spatial variability in property values. And so that's an interesting feature. And so I was thinking about property values for the application as just, there is some individual level component and there is confounding due to individual level factors. And then the spatial modeling isn't going to help you with that aspect of the confounding. But that is an interesting idea to decompose your confounder into the individual level component and a spatial component. And then the individual level component can maybe help you with individual level confounding. But I don't know how we'd have information on that without actually having it measured. So I think I might have even started with that in terms of the simulation, and then I ended up simplifying, try to get something that I could wrap my head around more. But I agree that practice, at least for the property values, it's not a purely spatial confounder, and it probably does have the individual component to it. So.
And then I just wanted to make a quick comment with regard to Sandy's question about the impact on power that comes from adjusting for the spatial component. what's relevant there, and I think Sandy may know this because she's reviewed papers that had this this factor. The Fisher information is driven by how much variation you have in the predictor variable. So if you adjust for other predictor variables, the impact of collinearity is to reduce the dispersion in that variable of interest. So you have lower variation in that, you therefore have lower power. So it's not an issue of bias per se, it's an issue of you're increasing the variability in the estimates of your coefficients. And so that may have been relevant for how the estimates are jumping around they went from negative to positive. That might not necessarily have to do with bias reduction. That could just be increased variability.
Yeah, I mean, I think that, yeah, in terms of the application, I think you're right. I mean, I think because you're adjusting for something, they're collinear, you can see, yeah, that will inflate your standard error a lot. And also you have a lot of variability in your estimate. So that also could explain jumping. I think I pulled this up just because what you were talking about is if you adjust beyond if you don't adjust enough, then you have bias. And if you adjust too much, then you've removed bias, but then you are adjusting for lots of unnecessary stuff. And so you increase your empirical standard error of your estimate. So it's something that you don't really know what that is. And so that's why we're trying to target the estimation of that to try to get that balance. But maybe there might be other methods I was kind of thinking of that kind of are jiffing off of this theme. Like you could kind of pre-process your exposure data to remove spatial variability. I think if you think about the EPS approach in general, that this idea that you're estimating the non-spatial component epsilon x, because you've removed the spatial component, you're removing some variability. So if there truly is no spatial confounding, and you try to do this approach, then you're removing some variability, and so you're reducing your power. And so that I didn't show those results because I also have results from if there's truly no unmeasured confounder and you do these things, then there's no free lunch, so you get the increased variability, and there was no bias initially, so you don't get any benefit. But so I think if you kind of felt like we don't have unmeasured spatial confounding, then doing this wouldn't be useful. But I think there's often the sense that there is unmeasured confounding, especially with these, like I said, these EHR studies where we don't have the good SES measures.
Irva has put an interesting question in the chat. I could read it aloud if you want, but Irva, if you're still on, would you like to pose the question yourself?
I can see it now. I'm just taking a look now.
Okay, well, basically she asks, is the increase in bias telling us in some way that it's a collider?
So I think I need to think about that, because for the cross-sectional example, things could be in different directions. It's very, the timing isn't clear. So the question would be, let me try to think. So if we have our exposure, which is the built environment, and then that affects SES. I think we did think about the fact that maybe the underlying construct of SES is not affected by your built environment, but property values is definitely not a perfect measure of that construct. Property values actually can be affected by your built environment. They build a park next to you, your property value goes up. But in the property values, we didn't see, I guess we don't know what the true bias is in the example, which is challenging. But the property values adjustment didn't go in the same direction as the spatial adjustment. And I don't know how space itself would be a collider without thinking about what the unmeasured spatial confounder is that we're trying to use space as a proxy for. So I'm not totally sure in this case.
Well, any other questions about this part of the seminar? Well, thank you again for that. I'm going to pause the recording at this point. And we can move into a discussion of BKMR if anybody would like to hang on into the at this point.